So I'm not done grading that exam yet, but in the process I have made through grading, I've made a decision about what I want to do with the next week. So let me show you what that is. So previously, this week we were going to start in on the topic of the topology of the real line, which, if you like, is introducing a new notion called just openness and closedness of sets. And in a field of mathematics called topology, you just abstract away the notion of what is open, what is closed, and it turns out that's enough information to do most of real analysis. And now you can do it in a much more broad setting. And my goal with that was going to be to hit the notion of what it means for a set to be compact. And then a lot of the proofs from then on would be topological in nature, using this notion of compactness. So what I've decided to do instead with this week is you have in front of you like a very broad strokes. Let's talk about how you write proofs, how to interpret the statements you're trying to prove and figure out what the proof should look like, that kind of thing. I'd like to spend this week, today, thinking about just stuff in that packet. Eventually the stuff in that packet will be like homework that I'll collect. There are a few proofs in there to write. On Wednesday we'll do the same. We'll talk about that packet. You'll be able to ask me anything you want to ask me. And then on Friday, I'm going to compose another version of that midterm, and we're going to take a version 2 of that midterm. Does that sound like a plan? Once I get you, yeah.
Does that grade then replace our original midterm grade, or how does that work?
I'll figure out that. I'll let you know on Wednesday. I'm going to decide exactly what those rules will be once I actually have numbers down. Because like if someone got like a 90% on the midterm, then there's not a huge reason that they need to do it again. They've demonstrated most of the knowledge. So I'll figure out exactly what I want the rules to be. And some people may wind up having an off day as a consequence. That seem okay? Yeah.
Does that mean the midterm didn't go well?
Yes. Yeah. For a great many people, I'm not done grading them yet, so I can't. Enough of the write-ups was suggestive enough that there's some content being missed, but I think we just need to slow down, take a pause, and go back to basics. That is just, how do you prove statements of the type that we want to prove? So, one thing I'm also going to do is I'm not going to repeat these because I need to be grading them. And if you take them now, then I won't be able to keep grading them. But I am more than willing to let you look at them quite faster today. So, you have those. Maybe I'll give you a small number of minutes to see what sort of comments I made. So for a lot of these statements, no, that's it, recorded. It's already recorded, okay. The type of thing that you need to prove are statements that have some quantum context, right? If you want to show this set is a subset of that subset, you need to show something really specific. So if you want to show bullseye, you can't see, but I absolutely miss. here's something which is at least close to what was on the midpoint. What do you need to prove in order to show? What formal statement do you need to show? So what does it mean to be a subset? Yeah.
Every element of the left-hand side is an element of the right-hand side.
Nice. So what do you need to show? To show this. You need to show because of course that's what you need to show. That's what it means to be a subset. So if you want to give a proof of a claim like this, a proof of something about absolutely every element of a set, you need to at some point consider absolutely any element of that set. So you need to have a line like doesn't matter what it's called. And then you need to show that that element is in here. But including that line or something equivalent to that line, let y be in there. It doesn't matter if it's called a y or not. Is a line that's essentially necessary. Without that, there's no way that your proof will achieve what it needs to achieve. So with that in mind, let's just do a quick overview of how to prove types of statements. If you want to prove a universal statement, and the for example was going to point it down here, it's going to be all of the typo issues that abound in my notes because this is the first time I wrote this document. So you need to start by considering an arbitrary representative of the collection of elements you're going to prove something about. So in this case, you need to prove something about absolutely every element of this set. So you need to start to consider any y in that set. If you want to prove this claim, for every natural number n squared minus 3 is not a multiple of 4, then what should your first line be? What sentence do you need to include? Yeah.
Consider any natural numbers.
Yeah. Right. So you all are being quite quiet. But so far that seems reasonable, right? If you want to prove a universal statement, you need to consider any possible representative of the thing you want to show something about. And we won't give a proof of this, but God damn it. You guys are just going to let me do that?
I was about to ask.
I guess I haven't written much yet. But
Yeah.
cool. So, if you make that consideration, any natural number n, and what do you need to show about that natural number n if this is the statement you want to prove? Yeah.
So that n very much is now.
Yeah. On the other hand, let's suppose you wanted to prove an existential statement. So you wanted to prove that there exists a thing that has some properties. If you want to do that directly, it suffices to come up with an example. If you want to prove that a thing exists, well, you just need to give a thing. That thing will exist. And then prove it has those properties. If you want to prove a statement like this, there's some big N in the set of natural numbers such that for a little n bigger than big N, that inequality. And so that's obviously like one of the steps in proving a limit, right? So let's suppose you had a statement like that. Well, you just need to come up with an example. So your horse line will be something like let big N be equal to, and then something that you'll figure out once you've done some scratch walk off to the side. But that sentence, let big N be this, is important. Because you need to have a trace of big N if you want to show a big N exists. And then finally you need to show that for little n bigger than big N. Fair enough. And maybe the other thing that I just want to push through as a reasonable proof technique is sometimes in the course of trying to prove a thing, you'll know that one of two things is true. When you're in that type of situation, a case-wise proof is in order. You get to assume either one of those situations. So let's suppose you did want to so let's suppose that you needed to prove this claim. If little x is in x union y, then f of x is in f of x union f of y. Well, if there's the thing you want to prove, what's the thing you get to assume? You want to prove an if-then. You want to prove if the hypothesis, then the conclusion. So you get to assume the hypothesis. So if you get to assume x is in x union y. And let's just expand that out until we get to this or statement. If x is in x union y, then what do you know? Yeah.
X is in X or X is in Y.
Yeah, absolutely. So here's a situation where you know one of two things is true. You know either x is in big X or x is in big Y, or both, but that's built into the word or because we're mathematicians. So one of two things is true. So now we can walk case-wise. So here's a strategy. Case 1. Assume x is in big X. And we won't finish the cases. In each of those cases, what is your goal? What is it that you need to show? Yeah. Yeah. And in the other case, you have the exact same goal. People feel pretty good so far? Oh. Yeah, sorry. That's too much. It's okay?
Yeah.
Cool. All right. So I was just talking about if you have an or statement, you get to assume. And let's see this in action. Let's suppose you wanted to prove this set containment. If you like, this is going to be line by line the proof with the motivation for why each line is what it should be. So if you want to prove that set containment, well, what is it that you need to prove if you want to prove that claim? Yeah.
Every
Every element of f of u. I'm going to say union instead of or. They're definitely related concepts. Yes, so the thing handed out was this document that says something like review after midterm 1, which I think was out on the table, right? Cool. The idea is I want to... wait, Simon, is it the... It's not the first Monday of the month, right?
Oh, crap, I couldn't even tell you.
No, it is. Okay. Okay, so we don't need to worry about that area. There is one, right? Am I just hearing out ringing noise? Okay. Neat. So that's a universal statement. I need to show for everything in this something happens. So if you want to show something about absolutely every element of a set, what's the next line that you must include? Oh, yeah. Sorry. Thank you. Yeah. Yeah, absolutely. And let's just remember the goal. So this isn't something that's necessarily a line that you need, but your goal is y should be in f of u union v. So carrying on, we get to know y is in f of u union f of v. So that's an assumption we have now. If little y is in there, then let's try to make sense of that. So right now we know y is in f of u union f of v. So if y is in f of u union f of v, what is it that you know as a consequence?
Is that a union or a v in between the two?
It's a union. It's just polygon. Yeah. Yeah, and that's the relationship between union and or. But you wouldn't say you there, you would say or. Oh, that's supposed to be here. Okay, I'm getting ahead of myself. Neat. So we know one of two things is true. That's a reasonable example of a time when you could use a case-wise proof. If I can prove a thing is true for everything in the case that y is an f of u, and I can also prove it in the case that y is an f of v, then I'll get the desired result. Nice. So let's do that. So let's assume y is in f of u and go from there. All right, if you know that y is an f of u, then what do you know? What's it mean to be an f of u? Yeah.
Does that mean that u is in one of the other sets? I forget.
It's going to be a subset of the domain, but that's not specified in the problem. Yeah.
Okay.
F of y is in u. That's pre-image, unfortunately. So let's write that down. That's worth writing down too. Not for this problem, but so f of u is all of the outputs which correspond to inputs in u. So let's just write that down. That means that there's some input in u that corresponds to y. And now you just need to write down what corresponds to, but I really mean is f of that input is equal to y. So let's write that down. Thus, for some little u in big U, f of u equals y. And if we remember the goal, I'm going to play this game where like the goal is going to be on the board and we'll try to trace our way back. Well, no, I can put it on the table. The goal is y is in f of u union v. And let's just try to figure out what that means. By the exact same logic, what does it mean to be in f of u union v? So y is in f of u union v means that, yeah.
There is something in union v, like a multiple something to that.
Nice. So that means this is actually our goal. So if I know there is some little u in big U, which satisfies that f of u is equal to y, and this is what I want, what seems reasonable? Let's see. I have f of u equals y. It looks like I want f of u equals y. That's good. I have u is in big U. I want u to be in big U union big V. Is the u I have in that set?
Yes.
Yeah, great. Let's write that down. Since little u is in big U, little u is in U union V. So, as f of u equals y and u is in U union V, that make sense? And what do you think? Is the other case going to be pretty the same? So I'm not even going to bother doing it. All right, when you do something in one case and the proof in the other case is literally the same proof, you don't need to write down the same proof twice. You can say it's the same proof. People feel okay right now? Hopefully nothing too deep or too shocking today. Yeah.
I'm kind of curious why you say that, but why then you say that you do that because we kind of have a straightforward statement that you kind of say big view or V and similar reasons, so you
Yeah.
okay.
Yeah, so it would be. Yeah, so the proof would be like the same except all the big U's and big V's are slightly different. Yeah, so you don't. The proof really is the same. You don't need to do it twice. Cool.
Would that be something you could use on the homeworks?
Yeah.
So it looks identical, not doing it.
Yeah, but if I don't believe you that it's an identical proof, then I'll be upset.
Okay, fair enough. Follow it.
So, I mean, you should at least stare at it and say, well, if you took that proof, replaced all the big U's with big V's, would it give you the desired result in this case?
Maybe I still don't know the answer, but it seems like that.
Let's see. If you assume that y was in f of big V, would there then exist some little u in big V with f of little u equals y?
Yes.
Yes? So far so good. That little u is now in big V, so is that little u now in u union V?
Oh, okay.
Yeah.
Oh.
Next line follows unchanged, so you get that.
Fancy.
So if it is literally the same proof,
Yeah.
you don't need to write it twice, but you should at least read through the previous proof and see that it is the same proof again.
Okay.
All right, so the next thing I wanted to hit, because there was more struggle with this on the exam than I wanted, is what does it mean to negate a statement? When I say I want you to negate a statement, I just want you to tell me what not that statement means. So, if so let's put together how you negate certain statements. So let's start by negating and. So here's a statement that's false. 4 is a natural number and 5 is even. Is that a false statement?
Yes.
Yes. Why is it false? Yeah.
Because one part of the and is false.
Yes. That hurts. 5 is not even. So if you have two different statements that are ANDed together and you want to negate that statement, well, the way that would fail is if even one of those two statements is false. So not P and Q is equivalent to not P or not Q. Parentheses, parenthesis. Cool. So if you ever need to negate a statement and it's an and between two things, you can. You just negate each statement individually and then replace the and with an or. That's what this says. Let's talk about negating ors. Is it the case that -2 is a natural number or 5 is even?
No.
No, because both of them are false. If you have any statements P and Q, if you negate P or Q, you negate the statements individually. You replace the or with an Q. Yeah.
So our logical operations are iterative throughout the whole statement, so every piece gets iterated over, right? So the or goes to an and, the P goes to a not, the Q goes to a not Q.
Yeah, think of it like distributed. So I'm going to try to walk from the outside in when I negate things.
Okay.
And we'll see that once we get to a complicated statement in a few lines. If-thens. So here are two statements. I guess I should let you pick which one is true and false, but it's labeled. If 2 is even, then 2 is odd. Is that true or false?
False.
False. Because 2 is even, but 2 is not odd. So the assumption is true, the conclusion is false. So this if-then statement is false. Because the hypothesis is true, but the conclusion is false. The next one, if 2 is odd, then 2 is even. Well, notice the assumption is false. So whenever you see an if-then statement with a false assumption, the whole if-then statement is automatically true. That's just how you incorporate if-thens.
Oh, well, that's super strange.
So
Is that like the purple unicorns example, or it's like a vacuous truth?
If I am a purple unicorn, then I am a green dragon. because I'm not a purple unicorn, as far as I know. So you can't make any conclusion. The hypothesis is false anyway. So the whole if-then is just regarded as vacuously true. And that's what this is. So the payoff here is I'm going to negate an if-then and get a particular statement. So that's on the next page. Let's negate an if-then. So suppose you want to negate if P then Q. For an if-then to be false, the hypothesis has to be true and the conclusion has to be false. So if you're ever negating an if-then, that means P and not Q needs to be true. If P were false, then you're talking about a statement that's unrelated to the if-then. You can't prove that it is not the case that every purple unicorn is a green dragon by starting by considering any zebra. It's not relevant. And finally, if Q were true, well, then the implication would hold, right? So that's what you need to prove if you want to disprove an if-then statement. So, we're walking towards negating a complicated statement, which we will in just a moment. Let's talk about negating universal statements again by thinking about examples. Here's a statement. Every month has exactly 31 days. Is that true? Why is that not true? Yeah. Awesome. There is a month with So this tells you how you negate statements that are quantified. If you want to negate a universally quantified statement, you need to find a counterexample. Not for all x in x, p of x is equivalent to for some x in big X, not p of x. Oh, that should be a little x. That should be a little x here. Well, here, p of x is some statement that's either true or false about elements of x. The statement could be little x is a purple unicorn. If you want to negate an existential statement, well, let's figure out what to do. Here is a statement which I claim is false. There exists a month which has... Oh, well, it's also grammatically incorrect. There exists a month which has fewer than 28 days. So that statement's false. Tell me why that statement is false. Yeah.
All months have at least 28 days.
Yeah, the shortest month is 28 days long. So every month has at least 28 days. So if you want to negate an existential statement, if not there exists an example as true, it must be that absolutely everything in consideration is not an example. So if you want to negate an existential, if you want to negate there is some little x in big X such that p of little x is true, that is equivalent to for all little x in the set big X, not p of x is true. All right, so now let's put this all together and negate something complicated looking. Oh, cool. So let's negate this statement. So let's determine what not all of that means. So the first thing we see there is for every epsilon bigger than 0. So that's a universally quantified thing. We are saying it is not the case that for absolutely every positive number some stuff happens. What happens when you negate that universal quantifier? Yeah.
You get for some epsilon less than 0.
So this right here is, if you like, specifying what set the epsilon lives in.
Okay.
So the epsilon is still going to be bigger than 0. It will become, for some epsilon bigger than 0. And then I'll negate all of this. For some epsilon greater than 0, not there exists some big N such that for all little n in N, if little n is bigger than big N, then absolute value of a sub n minus L less than epsilon. All right, so now we'll just carry down that for some epsilon bigger than 0. Next, I see there does not, there exists some big N such that some stuff happens. So this says there does not exist any example of a big N satisfying these conditions. What happens when you negate that existential statement?
You get a for all.
You get a for all. For some epsilon bigger than 0, for all big N, and then the rest of this still needs to be negated. With me so far? So inside of the tank, it is not the case that for absolutely every natural number some stuff happens. What's the negation of this? Yeah. There exists. So, copying all this down, for some epsilon bigger than 0, that's really badass. For all big N, and for some little n in the set of natural numbers, not if little n is bigger than big N, then absolute value of a sub n minus L is less than epsilon. All right, so now we're down to just negating that if-then statement. How do you negate an if-then?
Go with P and not Q.
P and not Q, where P and Q are the statements that are on either side of the then. Cool. For some epsilon bigger than 0, for all big N, for some little n in big N. And now I think we can negate these individually. Well, leave one of them alone and negate the other individually. So I keep the hypothesis the same. Little n is bigger than big N. And I negate the conclusion. Nice. Cool. And so now that we've written that down, each one step at a time once, I don't think it's often going to be necessary again to write down absolutely every step in negating a statement. right? That wasn't much complicated interplay. Each exists became a for, each for all became an exists. If then became an and not. So, particularly in light of page 1 of the exam, was that example useful?
Yes.
Okay, cool. So, what is left in this document are a few exercises, and this is where the actual meat of the document is. You're going to prove some things. But, well, here's the game. Every line of the proof is provided. But, not in any particular order, and in this case, I've also included all of the lines of the opposite container. So here's the game. Let's try to, possibly by staring at these and checking things off on the list, and by thinking about how the proof is stood, let's try to come up with this proof. That I equals A, B, and any function F from A to B, and then U and B contain A. That contain A. And I think, so the homework for today and next time really is just this document. So we'll do some of it in class, but I think I'll devote most of the next time to is you all thinking about these things at whatever pace you want and asking me any questions you want to ask me. Let's try to start it on this one. Let's try to put together this proof. What seems like a good first line? Yeah.
What A and B be set, and that's the assumption from A and B with U and B being a subset of A.
Yeah. I think in the interest of efficient use of time, maybe I won't write anything. That seems like an excellent first step. Write down the assumptions. What seems like a good next step? Yeah. We want to show this is contained in that, so this is probably a good next line. Yeah.
And if we follow immediately from that, we say, since we considered any y in that union.
You're talking about like the front whole point down to the top? So let's leave the whole sentence. That's probably seems like a reasonable
Oh, and
term.
show that.
Yeah, we haven't showed that anything yet. So I think that's more like the last line. But maybe we can highlight that. That's a good last line. And yeah.
But 3 down from our first bullet, since y is at u using v, the definition of the equal means that there is some x in u using v with f of x equal to y.
That seems good. Cool. How about that? Right, but I definitely know now that X is in U union V, so it's a reasonable thing to combat. Nice.
u and f of x equals y. Y is in f of u, and then the one below that as well for these statements. That's two different cases.
Yeah, cool. So those are definitely relevant, and they'll come sometime soon. But do we right now know that x is in u? So we can't use that yet, but look a little bit above, and you'll see something that looks useful to connect those dots. Yeah?
Yeah, I was just saying,
So let's do that. So there's 4, there's 5. And so it looks like now we can use the Forster layers.
do we move on to the second piece then? Or no? I feel like there's enough bullet points that we're still missing something with the first case, but I don't.
Only a very small something. So there are two different strategies. Like you could say, okay, so in this case, y is in f of u. In the other case, y is in f of v, but either way it's in the union. I'm just going to include that in a separate case, in a separate step in each case. So if you like, here's what I want the next line to be. You could definitely say, like, move right on to the next case and then say something like, in either case, we have this conclusion. But maybe it's also useful to actually state the conclusion in each case. So, what do you think? If we can get down to, like, is that basically what we needed to show about little y?
Yeah.
So this one was definitely done with that. We've made it to the conclusion we needed in this.
So onwards and upwards to the next case.
Onwards and upwards to the next case.
Would we, in the second case, we assume that x is in V?
That seems good. And I guess that leads us right into the reasonable next step. Yeah.
The one that's since x is in V, we have f of x is equal to y, and y is in f of V.
Yeah, cool.
Look, isn't that a 9?
Isn't that a 9? Yeah, 8 plus 1 is 9, isn't it?
Hop along since y is in f of v, y is in f of v union f of v.
Nice. Is that exactly what we needed to show in the second case?
Yes.
Nice. So, we're done with the cases. Let's maybe just announce that we're done with the cases. The proof is basically done at this point, right? So,
For this containment.
notice, this doesn't claim equality.
Oh.
The other containment is true. And all of the steps for the other containment are in the list.
Oh.
I just didn't want this exercise to go on twice as long as necessary. So I think to wrap it up, in either case, you get this result. And now we're ready to finish the proof. So, we're about at time. The rest of this document is more examples like that. And that document is the homework for at least today, probably Wednesday as well. And then on Friday, you have that exam. I'm going to give a mulligan on the exam.
So we're going to redo the exam again on Friday?
We redo the exam for the first time. You haven't redone it yet? Yes, there will be a redo on Friday.
Okay.
But before you go, don't take the exams with you. I'm not done grading them yet.
Oh.
If you don't give them back to me, then I can't enter a grade when I finish grading them.
For a moment. So then, what,
I know what I did wrong with this. I obviously did. I was so trying to be fast on it that I just kind of said, okay, let's keep like the last part. That's what I had.
Okay.
But Harvey's like,
That was a very common.
I have not been ahead of this course.
I mean, I already felt like I
And this is the first time since the beginning of this, I'm like, okay, what's next?
and so
And I haven't had something like.
oh, okay, I just got it. Okay, thank you so much.
So, yeah, so that issue was, given the discussion we had that, it was a really complicated.
Yeah, absolutely. I really just didn't. I didn't even think to look at it twice. When I was going to the door, right? So.
Yes. No, that's fair.
Go team. We studied together. I thought I did. Oh, I feel like I did horrible on that thing. Like I'm looking at it, I'm like, it's more points than I thought.
That's good. That's a good spot to be in.
That's a good spot.
The lower half.
Bury that bar in the dirt and you'll feel great about walking.
Gives me something indicating that you started the paperwork. That you started whatever you need to do to get time on that. And then on Friday, what I'll do is after the